Good afternoon, everyone. Thank you, organizers, for this opportunity. Um, Today, I want to talk about index distribution of short-range Riesz gas. This work is done with Manas, Anupam, Satya, David, and Gregory. And this work has recently come on archive now. Uh, so what do I mean by index distribution? Let's say there is a line, there are many particles on the line, or let's say there are points on the line. If they are distributed from some random distributions, I want to understand what is the number of particles and the distribution of that less than W. I mean, what is the distribution of the position, number of particles below W? And for a non-interacting system, it's clearly a Gaussian because you're adding Bernoulli numbers, whether they are inside or outside. And the variance will be proportional to total number of particles. But what happens if there is interaction in the system, in a sense that these random variables, maybe let's say, are correlated, or this particle is interacting? This index distribution actually is part of a broader class of problem called the full counting statistic, which measures the number of particles, the distribution of number of particles in a certain domain. It could be any domain. And this is useful for studying both equilibrium and non-equilibrium properties. For example, we can understand the entanglement entropy for free Fermi gas using the full counting statistics. In a similar way, we can understand whether the system is hyperuniform or not. By hyperuniform, I mean the fluctuations becomes extremely less. Or additionally, this is a good experimental variable also, because instead of keeping track of each particle, what they are doing, if you just look at the cloud of gas, let's say, maybe we can tell some features about the underlying system. And in that sense, it's a good experimental variable. Also, despite these interests, not a lot of analytical understanding is present, except for few cases like Dyson's log gas, where the particle interacts logarithmically, or the one component plasma, which is a 1D Coulomb gas. For that, it's very well understood. In this work, what we have tried to do is to understand the index distribution for short-range Riesz gas. By short-range Riesz gas, I mean the particles interact as a power law with an exponent k, and k here is greater than 1. Because of k greater than 1, it's short range. If k was less than 1, because we are in 1D system, if it was smaller than, it would have been long range. And here, all the particles interact with all the remaining particles. So that gives indirectly, it's probably not completely short range because it's interacting with all the particles. For such a system, the energy can be represented by two terms. This is the potential energy, and this is the interaction potential. Now, this is a repulsive interaction. The repulsions would try to throw away particles to the infinity. However, the trap will not let them go to infinity. The trap will try to push them at the origin, right? So as a result of this competition, what happens is this particle settle down on a typical length scale, which is of the order n to the power alpha k. And because of this length scale, what we find is the system is actually super extensive. The energy is super extensive. Because of this super extensive nature, we could do some computation. And this is going to be very important. Additional ingredient to do our computation is to understand the free energy, the energy in terms of coarse grained variables, which is density. We find that the density has again two, in the energy in the field theoretic sense, has two terms, potential energy and the interaction energy. And interaction energy is local. This is another ingredient which helps us in solving our problem. Using this local energy, we can compute the density of the particles at equilibrium when the temperature is order 1. What we find is the density is we see is the density has a finite support, and generally we would expect for finite temperature systems to have slightly decaying tails. However, that does not happen here in a thermodynamic limit, because energy is super extensive and entropy is extensive. And again, this is another ingredient which is going to be useful. Now, for our study, we want to study, of course, index distribution, which is number of particles less than W when the system is in Gibbs equilibrium. Clearly, when the system is Gibbs equilibrium, the probability of any configuration is given by this. There would be many configurations. Let's say there are m particles to the left of W. We want to find what is the probability of such a configuration. There could be many configurations, but the configuration which will be, the probability of the such a, probability of m particles to the left of W will have sum over all the configurations which has this kind of, this macroscopic configuration. And that sum is going to be dominated by the minimum energy configuration. And this computation can be done more conveniently in coarse-grained variables in terms of densities. So effectively, it turns out we have to find a density profile which minimizes the energy with the constraint of m particles to the left, and that is the saddle point density. And we find this saddle point density depends on the fraction of particles to the left of W and the location of the wall also. We see that when at equilibrium, when there is no constraint, we just want to, when there is no constraint, there is this mean curve. If you put a wall here, how many fractions are to the left of W is described by this line. If there is more particle than the equilibrium, the density profile looks like this. And we check it numerically, and we find that it actually matches. But if there is less number of particles, we find a density profile which looks like this. Here clearly the density here was less. Now the density has become smaller here. As we keep reducing more and more particles, what we see is that there is a whole region formed. The region here, the particles here will, the density profile here will start shrinking and shrinking at exactly C equals to C bar line. When it touches this line, this region actually, this density profile touches the wall. And if you go slightly lower than that fraction of particles, we get a whole region here. This whole region has interesting feature which I'll just discuss, and we compare it with Monte Carlo simulation, we do get the result. So now that we understand these density profiles, we want to understand what is the distribution of such a configuration. It's nothing but the Gibbs weight with that density profile. What we find is the probability is actually given by a large deviation form with the speed n to the power 1 plus 2 alpha k, and the large deviation function which basically says what is the amount of energy required to create such a configuration. Starting from a ground state, how much energy, extra energy do you require to create a configuration with Cn particles to the left? And we find this large deviation function looks like this. As let's say there is 0 particles to the left, as we are increasing the number of, as we add particle to the left, what we see is the energy is going to reduce. And at this point, when we touch this whole region, when this whole region disappears, we find that there is a third order phase transition. And as we go down further, we encounter this another density change, change in the shape of the density. And we find that here it's actually normal, it's quadratic. I should have explained with this, but anyways, as we cross for a fixed W, if we are increasing C, I'll be done. Increasing C, we'll encounter this line first and this line. As a result, what we find is near the C equals to C star line, the typical fluctuation turns out to be Gaussian, and the variance of the variance of the particles, this number is proportional to n to the power nu k, where nu k is 2 minus k by k plus 2, which depends on the interaction. And we find that this is actually very different from the non-interacting case. We compute the variance from Monte Carlo simulation and see that they match quite well. So in summary, we have computed the variance for a interacting system, this index distribution for an interacting system. We find that the variance is Gaussian and proportional to n to the power nu k. And we find an interesting third order phase transition, which is actually present for long range systems also, but that happens at C equals to C star. Thank you.
Questions?
Yeah, so you showed that the energy is not extensive, something like that.
Yeah.
I had the impression that you get non-extensivity when you have long-ranged interactions, but your model is short-ranged.
Exactly, that's why. Even though between two particles it's like short range, because of all-to-all interactions, it's effectively, it's effectively like I could say it's not a truly long-range model, but it has some long range nature to it because it interacts with any particle, even if it's far away, is going to interact, and there will be all n interaction.
Okay, let us thank the speaker.